Okay, I'm going to draw some connections between a few things um, that should be fun. So one of the talks I gave at Microsoft's Channel 9 was that you can think about a wide range of finitary monads essentially as just colored parens. So the unit for some monad uh, at type A is just to put your A element between two parens, and flatten is to roll up all the parens. But you can also look at this from the point of view of protocols. So for example, HTTP is interesting in that it's completely flat. You have a request, which you can think of as an open paren, and a response, which you can think of as a closed paren, and nothing goes on in between, which was sort of why cookies had to be invented, was to be able to put things in between those in order to do sessions. And sessions you can think of also as open, as an open paren, and then a bunch of work requests, and then close paren. Um, and you could imagine nesting these as much as you want. So for example, um, something like this, but this is a very one-sided conversation, right? Where only the client may initiate a question, and the server must always answer the question, right? So that's perhaps not the most satisfying generalization of HTTP and sessions. But you can imagine very ordinary conversations, such as ordering a coffee, where the server responds to the client's initial request by asking a request of their own. So, can I have a coffee? Sure. What size? And then when the client has responded with what size, then what kind, and then the client can respond with a latte, and then what kind of milk do you want to use in your latte, and so on and so forth. So you can see that there are very natural client server kinds of conversations, where the server initiates a request as well as the client. So we could change up our representation in terms of parentheses by imagining that there are not just so you can imagine a table, right? So there's client and server; those are two different roles, and then there's request and response, which are different kinds of actions associated with those roles. So the client request looks like a round paren, but a client response is a square paren. And a server request is a square paren, and a server response is a round paren. So then if we just map that idea over this conversation, we see that the shape of the conversation, right? So the client makes a request here, which is the client request here. And then the server makes a request, right? And the client responds. And the server makes a request and the client responds, and so on. And then finally, the client responds to the initial question. So you get this balanced expression using this approach. So let me just stop there and see if that makes sense to folks.
So the first example was HTTP, and the second is WebSockets, right?
That's right. That's right. And then, but this is a little bit. This is more general than either of those.
Oh yeah. And much easier to understand.
I think so. I think it's relative.
Oh yeah.
Um, now notice that, there isn't further recursive nesting, but you could imagine that in more technical conversations than just ordering coffee, such as a requirements gathering, you might have arbitrary levels of nesting, right? So when a server asks a question, then a client responds by asking a question, and so on and so forth. So you could have potentially arbitrary levels of nesting as well. And so you can ask, is there a shape to all good service conversations? And one thing that's important to observe is that you want to distinguish, like in this conversation, you could reorder these, right? So the client, the server could ask what kind in front of what size, right? So there's a kind of commutativity in some of this, but not in all of it. And so you want to be able to distinguish between actions in the session that are commutative versus actions that are not. So we'll give them colors, right? So the non-commutative will be red. So now we have 3 dimensions, right? We have client and server, request and response, commutative and non-commutative, right? And this gives us a basis for a complete syntactic characterization of service conversations. So in particular, a service conversation is going to be a protocol M involving M commutative request response pairs and N non-commutative request response pairs. And we can define it recursively. So you can think of this in a lot of different ways. You can think of this as a data type specification, or you can think of it as a domain equation, or you can think of it in terms of grammars. All of them are equivalent, but essentially the idea is that a client request involving M commutative request response pairs and N non-commutative request response pairs can open either with the ith commutative or the jth non-commutative, and then have as many server conversations, server initiated conversations. So this is the client initiated conversation. This is the server initiated conversation. So the client can open the conversation and then kick off as many server initiated conversations. And then the server must respond to the client. And you can do this in either, the commutative or non-commutative flavor. So I is ranging from 1 to M and J is ranging from 1 to N. And then the server is just the dual of that, right? So the server can open the conversation, and then the client must close the conversation, and in between there can be as many client initiated conversations. And this is either in the commutative or the non-commutative flavor. So here's an example, right? We see that all parens are balanced in color, and we always have a balanced expression. Does that make sense?
Yeah, this is so nice.
Yeah, what is the S in the CS and the SS? What is the second S?
So this is client initiated conversation, and this is service initiated conversation. The S is you can think of as session. So the client initiated session, server initiated session.
Okay.
So I think, and the interesting thing is that you can connect this back to monads, right? So this is going to be monadic in a particular way, and it is also encoding a notion of sessions, right? So this gives us a way, for example, to directly connect the Oleg style delimited continuations. So you can think of these. So the delimited continuations monad identified by Oleg can be given an interpretation here, and I'll let you guys investigate that. If you don't see how it's done, then we can talk about that sometime. But you can also connect it directly to protocols. Now, obviously, there's an algebra, right? So the algebra of these conversations looks like, so you have, imagine that you've got two client rooted or client initiated service conversations and two service initiated service conversations. Then we have two operations which are essentially polymorphic, right? So you've got the red and the black star, and the star takes three arguments. It takes an index, and then it takes the two conversations. The index picks out the kind of paren that you use, and then you just simply deposit them in between the parens, right? And this makes sure you have the strict alternation, right? So, and then you can also do a cons, right? So you can think of this like append, or, well, this is not quite append. There's also an append, but you also have a cons, right? So this is effectively some kind of list. We can cons on an element to a list, which means we just open C up. So we figure out what the opening bracket for C is. We deposit the S in, we put the elements of C in, then we find the closing bracket for C, and vice versa for C and S. Is this clear? Does this make sense?
So cons is like creating new message, or
yeah. So cons is like taking this conversation here and putting it inside this one as the first one. So if we go back to our example, you'd have some square bracketed thing here, cons this. So you take this and move it out over the square bracketed thing.
I see.
All right. Now notice that you could restrict nesting so that not every flavor of client conversation is nestable under every flavor of service conversation. So that's one form of control that you could add to this algebra. And you could also make it possible to add new request response pairs. So that's that's another way that you could extend this theory.
So the cons.
Go ahead.
Sorry, that cons is that conjugate, or what is the cons?
Cons is in cons of lists. Consing an element onto a list.
Okay, so in physical terms, is that reflecting the interaction of the server with one particular client, or with one particular client session? What is it physically relating to?
It's taking what it says is here is you could think of this as a trace of a given a session, right? So this is a given session, and this is taking a server session and nesting it inside. So we can think of a given session as the composite of a session with of a whole. You can think of the whole client session as the composite of a previous client session with a server session. So, and vice versa.
Okay.
Yeah.
For restrict nesting, and this means we are creating new types of brackets, right?
Yes, that's the no. You're making it so that here in this grammar here, any of the server sessions, right? So any of these can appear between any of the round braces. And what we're saying is, no. It might be that, for example, the jth one is allowed between the ith one, but not any others. Right. So you can think of it as a composition constraint. And then the other thing is that you could potentially, oops, that's weird. You could potentially change these M's and N's, right? So here you fix the M and N, right? But you could potentially increase or decrease the M's and N's.
Mm-hmm. For example, we can maybe look at the structure of M and say, no, after this first message, the M must be something else.
Exactly. Yeah.
So, I mean, is it the same as then saying that that's how you would implement the non-commutative aspect? For example, if you're talking about latte, the conversations in that bracket need to be related to latte or not, or something around that, but not about size, for example.
Yes, you could certainly, you could do an implementation of non-commutativity with those kinds of constraints. Yes.
Okay.
Yes. And then you can translate any service protocol into rholang. So here's a sketch. I'm only doing the commutative version. You have to fiddle with it just a tiny little bit to get the non-commutative version. But so if C is some client protocol, then obviously you have to have a client that will accept the request. And therefore you have to have something that will send the request, right? So I'm using the square brackets polymorphically to translate both conversations and requests and responses within the conversation. So this is the translation of the request, and this is the translation of the response. So notice that the translation function, at least for conversations, takes X as a parameter. So X is some channel. So the client side is going to listen on the channel for the request, while the server side is going to send on the channel the request. Having gotten the request, then you will loop through the elements of C. And in parallel, you will send on the channel the response. Right. And then, so essentially every time you have a send, that's the server side. And every time you have a listen, that's the client side. Notice that, and here's a simple loop, right? So loop matches this with the case nil, in which case it becomes 0. So if you just had open close as in the case of HTTP, this whole thing would be a 0 in parallel with send and response, right? So sorry, I said client and server backwards. Here's the client making the request. Here's the server receiving the request and sending the response. Does that make sense?
Yes.
Okay. All right. And now if there are some elements inside, that means that list decomposes into a head and a tail. And so we want to prevent any stomping on each other's messages, right? So we make a new channel, a fresh channel. We translate the head and that's going to, that will give you your corresponding send, and then you loop on T. So that will take care of all the elements of T, right? So, and that's it. There's nothing else to it. You have to fiddle with it to make sure that you have a synchronous as opposed to an asynchronous send in order to get the commutative, the non-commutative version to work, right? So when you do the send, you have to have an ACK before you move on to the next element, and that will get you the asynchronous version. And so then the next step is you'll find that there's a behavioral type for all processes of this form, which I haven't written down, but I would leave it as an exercise. So write down a behavioral type for the processes of this form, and then that behavioral type, hint, 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 will look remarkably like this. And so that gives you a type verification for the these kinds of sessions. So that's basically it. Any questions?
Yeah, I think we should be able to use this for the Zulip R-chain to PostgreSQL link, right?
Yeah, I mean, that's too simple, right?
Yeah.
It won't get you a lot of mileage, but if you think, there's another thing to think about, right? Which is if you think about these kinds of balanced expressions in terms of transactions, right? This is really about transactional semantics, right? This from here to here is a transaction, and it's nested. So the thing that I think is exciting about this is the potential to have to have these governed by tokens, where tokens only become active when they're in a particular context, right? So this token doesn't even exist or isn't tradable until you've opened this paren, right? Once you've opened this paren, then this token becomes available, right? And then this token becomes available after you've opened this one, right? Do you see what I'm saying? So so that I think is quite exciting, and it's something that no one has explored to the best of my knowledge.
So things like escrows and all that could be implemented with this.
Yes, for example. Yes.
Or inter-blockchain communication.
For example, yes.
That would be like much simpler, because I was looking at the white paper and all the TLA specification. It's huge. So this is like perfect match.
Yeah, it's a very the idea is to keep it as simple as possible so that and anybody could understand it. And I think that the nice thing about it is that you can just check with your eyes, is this a valid transaction, right? Your eyes can see the balance.
Can you just say a little bit about how to write these behavioral types? Because right now I don't know how to do it, but I would like to.
Sure. So this thing corresponds to a listening. So let me find. Okay. So this one. This would be the X, and this would be any sort of pattern or shape that you put on the request itself. And then phi, well, remember, phi is going to have to be recursive, right? Phi is going to refer to what's allowed to be in here. right? And we know that what has to be in here is there has to be a send on X. And then this thing somehow has to match whatever we got here, right? So that is going to be this one.
Fee is the term that we want to type, right?
So hang on. This is the term we want to give the type to. Okay, and these are the formulae. So phi is a recursive, is the next part of the formula. So this represents, we know it's going to be a 4. We know that this is a spec of that says something about the channel that we're listening on, and this is something about the variable, the shape of the variable. And this is the rest of the formula. Okay, so we know that the formula is going to look like this, par, right? And why is it a par? Well, that's because there's the par there. So,
Okay.
right? And then you'll have similarly, whatever the spec for this was, that's gonna also spec this. And then you're gonna, and then there's a fee which is gonna spec that, right? So it'll look like oops. It'll look like bracket X, and then I can't remember, did I do? Yeah. So bracket X, and then you're going to have some kind of spec for the request. So I'll just put that in italics to distinguish it from that.
And when you say spec, this means another type specification.
Yeah, exactly.
Mm-hmm.
And then over here, we'll have bracket X, and then you'll have some recursive fee right here. So I'll just put I don't want to use F because that denotes, I'll use S for spec. Okay, so there's some spec that you're going to need here, right? And then you know that you've got to have an X here. And you've got to have some spec here, which I'll denote as S prime. And then you've got some other spec here, which I'll denote as, how about I call this one S, S prime, and S double prime. Right, so your spec, your formula, your type is going to look something like that. And you have to figure out what the S's are.
And S must involve typing the loop, and this will be the part.
Yeah, so essentially it's going to be a recursive spec, right? You know it's going to be a recursive spec. So each one of these, right, is going to be, so since this is client, each one of these has to be a server, right? So what you've got is an unlimited supply of servers, right? So potentially unlimited supply of servers. And then here, you've got the send, and then this. And so then the server is going to look like this, only flipped around, right? So you'll have a client spec and a server spec, right? And amazingly, it'll look like this, right? A client spec and a server spec.
Yeah, this is nice.
Right? And you can actually see the balance parens, right? There they are. There's the open, there's the close. Well, I think this syntax doesn't use the bang, but there's the open, there's the close. Sorry, yeah. In reality, there's the open and there's the close, right? Because we're talking about the send. This is the picking up of the send, and there's the response.
Yeah, and on the server side, it's probably very similar, right?
It's going to be perfect. Yeah, exactly. Yeah. So you should be able to figure out the type.
Okay.
Like that. There, like that. That's a little cleaner. Yeah. So, and so if you run into problems, just ping me on Discord or something.
And do you envision that we will write these behavioral types somehow together in rholang, together with the terms, or like on a separate place? I'm thinking like a Haskell style, or
you can do it both, right? So that it can be, you can have the type embedded in the term, or you can have the type separate and ask that the term match the type. So that's all I've got for today. Next week, I will give a short introduction to Clifford algebras. I will talk about how to embed the Clifford algebras as a data type in Rholang. Right, so imagine that it's just like any other numeric type, like big int or float or integer. All of those are types. So the Clifford algebras are another kind of data type that you could embed in Rholang. So I'll give it an introduction and talk about how to embed them, and then talk about how to do graphics using Rholang. And in particular, how to look at a variant of Rholang where the com rule is evolving as the program evolves. So it's a kind of higher order calculus where the rules of the calculus that itself, they themselves, they change. Which I think is kind of fun. In particular, I've been intrigued by Lee Smolens's idea that the laws of physics need to be able to evolve over time, and that's a thought that I myself had some years ago before I read Smolin. And if you think about the rules of the row calculus is like the laws of physics. If during the evolution you can modify the com rule itself, then that's the laws of physics evolving. Yeah, so more on that next time.
So we can have like a Rholang somehow. No, it's not the correct word, evolve, but like transform to lambda and forget about
yes,
producing.
You could absolutely have Rholang become lambda and get stuck in lambda. Yeah. That's a totally reasonable scenario. Well, I don't know if it's reasonable, but it's definitely something you can model. I will be looking at a restricted form where it's still always rholang, but the main idea is what constitutes either end of a channel will change, right? So then that idea is foreshadowed by the annihilation rule, because you can have many things that are either end of a channel, right? They just have to annihilate each other. And so you could have a channel with two different kinds of ends, as long as they annihilate each other.
Can we see, for example, rholang 1.1, some transformation are doing something like that? They're transforming, or
no, rholang 1.1 is completely static. Yeah, it's not.
But maybe I'm thinking maybe some kind of macros when we want to when we transform rholang in some way that we will not have exactly the same com events. So is this some kind of
oh, but macros don't do that, right? Macros just, you boil away the syntactic sugar, right? There's always some rock solid foundation underneath.
I see. I'm thinking maybe if we are doing some kind of optimization where we are really changing what com events will happen.
The main idea though is if you could keep changing what com events are. With optimization, you'll convert all things that look like one shape into another shape, right? But you're not gonna keep changing the kinds of shapes that that you could be, right? So this is like, yeah, it's protean in the sense that the shape is not fixed.
I see. What I'm thinking is basically a static rewrite, and
yeah. This is got another level of complexity where the rewrite rules themselves change. And I think that the situation where the Clifford algebras that I'm talking about will make it make sense a lot more, because I've like once you start doing that, all hell breaks loose. It becomes really difficult to reason about and really difficult to have intuitions about, or at least for someone like me. But at least in this limited case, you can kind of get a hang for what would be useful in terms of this kind of evolution. And it'll be clear once you understand how to do geometry with the Clifford algebras, how to do graphics like operations, then I'll illustrate how you could do some cool drawing by interpreting the com rule as a kind of line segment. Right, it's literally the connecting line between 2 points, between the ends of two vectors in space. And so then you might want to change what kind of vectors get connected, right? And so that actually changes the com rule. Now, this is a very, very heavy-handed way to do that, but it's in order to build up intuitions. All right. Thank you so much, everyone. We'll see many of you in Dev Stand-Up in just a few minutes.
Thanks. See you. Bye-bye.
Ciao, ciao.